So, let us get started with the lecture. One of the motivational questions we have to ask is, can we connect the various issues we studied regarding convergence and interpret this as projecting a signal onto the basis, right. I mean, this is where we are sort of leading towards, I mean, in terms of the Fourier expansion, right. So, the question is, can we connect these issues of convergence over L2 okay. Now, suppose f is a function that belongs to the square integrable functions. I mean, I am specifying the interval. Let fn of x equals a naught plus sigma k equals 1 to capital N a suffix k cos k x plus b suffix k sin k x. K goes from 1 to n, and we see this in the summation. Okay. Now, here ak and bk are obtained by projecting f, this is a function, this is the square integrable function, onto cos k x and sin k x. Now, we can interpret this as fn is the orthogonal projection of f onto the space Vn, that is f suffix n is the element in Vn, right, in this space Vn closest to f in the L2 sense. So, I will say maybe this is A space Vn, right. So, what it means is, now we are given some function which is square integrable function, that is, you take the square modulus of the square, integrate it over that interval, and that is finite, right, and consider those functions, and fn is basically f suffix n is the orthogonal projection. If you write it in terms of the Fourier series representation, that is basically the orthogonal projection of square integrable function onto a space V suffix n, right, and fn is an element in V suffix n closest to this function in the L2 sense, right. That is, if you look at the norm of f minus fn under the L2 sense, right, that that should be the closest. I mean, or that is, if you want to minimize that metric, right, in the L2 sense, then the expansion happens to be of this form. Now, let us formally put this here. Suppose f belongs to L square minus pi to pi, let f suffix n of x be equal to a naught plus summation k equals 1 to capital N a suffix k cos kx plus b suffix k sin kx, where ak and bk, right, ak's and bk's are the Fourier coefficients of f. Then if you look at this norm fn minus f under the L2 sense, right, this heads to 0 as n goes to infinity. So, the proof is basically involved, and we will discuss this proof later, but I think you get a sense of some geometry here, right. You consider some square integrable function, let fn be in this form, then under the L2 sense this this heads to 0 as n goes to infinity, right. So, I think the subtle issue is, what if you have points of discontinuity, right. The subtle issues points of discontinuities in f and possible extensions to overcome these. We will discuss this proof with a geometric interpretation, but before we discuss this theorem we will have to prove one more theorem, and I will state that result and then we will connect all the pieces together. So, my style of pedagogy here is more, there is a problem at hand, we try to look at the problem, what it requires, then we set up certain lemmas that is required, and then we will nest it within a theorem, right. That is the whole idea. I mean, you could start very formally with definitions and lemmas and theorems, and if I go in that route, maybe you will be lost a little bit in getting the intuitive feel as to how to go about things. So, slightly different than the conventional approach. So, we will revisit this theorem, but bear in mind. So, let us prove an easier theorem, and then we will use this result into the other theorem. If a sequence f suffix n converges uniformly to f as n goes to infinity over the interval a comma b, it also converges to f in the L2 sense. This is an interesting result. If there is uniform convergence, then it also means it is convergent in the L2 sense. So, let us prove this result. It is a very easy proof, we will get the idea very clearly. From our definition of uniform convergence, for a tolerance epsilon which is greater than 0, some positive tolerance, and integer capital N, absolute value of Fn of t minus f of t is within epsilon for all integers small n greater than or equal to capital N, and t belongs to the interval a comma b, right. This is our definition of uniform convergence. For all times t within this interval, this function is bounded within epsilon, and you have to recall the other form of convergence where epsilon depends upon, tolerance depends upon the point. So, this is uniform convergence, so it is not dependent on the point t. Okay. Now, let us consider the L2 norm of this. I have to put a t here just to be a little careful. Okay, this is basically integral a to b from our definition mod fn of t minus f of t square dt, right. This is by definition. Now, this assuming this property is less than or equal to epsilon, right. So, therefore, this norm is less than or equal to integral a to b epsilon square dt, and this can be simplified as epsilon square b minus a, right, and see how easily we were able to plug it assuming uniform convergence. If it was point wise, then we would have difficulty, because all of which for every time I would have to choose some epsilon which depends on the point, and then I have to look at some series, a summation of various such tolerances, and I might not be able to simplify it in this form, right. So, this is easy now with uniform convergence. Now, this implies the distance between Fn and f is epsilon times square root b minus a, right, and this is for all small n greater than or equal to capital N. So, since epsilon can be chosen as small as desired, Fn heads to f as n goes to infinity in L2. So, what does this mean? That means if you have a sequence which is uniformly converging, it is convergent in the L2 sense, right. I want you to ponder the other way around. Examine if convergence in L2 implies convergence uniformly. So, this is a homework exercise. So, I think you can construct a function and show one way. I mean, it is enough if you can give a counter example, if not you will have to prove this result if you think it is true. Now, let us slightly interpret convergence in the mean. There may be cases where Fourier series does not converge uniformly or pointwise. It may be useful to study if it converges in a weaker sense, that is in L2 in the mean. So, I already gave you a hint that this is a weaker notion of convergence. So, therefore, you know sort of an answer to the previous question. Now, let us consider a 2 pi periodic function and let V be the space of all square integrable functions from minus pi to pi, which means if f of x belongs to this space, it implies that integral minus pi to pi modulus of f of x is less than infinity. Now, from our inner product spaces, the inner product between two functions f and g is given by this quantity, where you look at the conjugate of g if it is complex, is a Hermitian inner product. Okay. Let V suffix n be the space spanned by 1 cos kx and sin kx, k equals 1 to n, an element in this space V n is C naught plus summa k equals 1 to capital N C k cos k x plus d k sin k x, right. This is our notion of the Fourier expansion. C k's and d k's or possibly complex numbers. Now, if you say some f n of x is say a naught plus summation k equals 1 to n a k cos k x plus b k sin k x belonging to this space, a k and b k are obtained by projecting f of x on to cos kx and sin kx, right. So, I think what we have to understand is we have to recall a lemma that we did in module 1, that is the basics of signal geometry, right. So, I just state this result as a lemma. If V is an inner product space and V naught is an n dimensional subspace with orthonormal basis set E1, E2 dot E suffix n, the orthogonal projection of some vector v belonging to the space V onto V naught is this vector V naught, this is space V naught, which is summation j equals 1 to n alpha j E j, with alpha j is the inner product between this vector V and this basis E j. So, we proved this result, and this is exactly the interpretation of the Fourier expansion. Right. At the undergraduate level, you might have just taken the function, just figured out that you want to multiply with cosines and sines and somehow compute those coefficients, and therefore, you have a Fourier representation and you would interpret that this is your amplitude spectrum, right. You look at the complex complex form of the Fourier expansion and then interpret that as the amplitude spectral density, and then what portion of the spectrum contains energy, what does not contain energy, and you would have interpreted that in your electrical engineering, but this is all the mathematics behind that. It is just another way to understand and interpret the representation in a linear algebraic form, and in what sense you take the inner products, there are subtleties, right. So, I think this picture should be very clear in your mind. So, let us use the lemma here. So, using lemma above, f suffix n is the orthogonal projection of f onto space Vn. So, this would imply that f suffix n is the element in V suffix n in this space closest to f in L2 sense. Therefore, f minus fn in the L2 sense is minimum over all g belonging to Vn, the norm of f minus g in the L2 sense. Right, this is the Fn is the element, this Fn which is the Fourier expansion is the element in the space Vn which is closest to the function in the L2 sense. Okay. And we want to bring in this L2 notion because it is a weak, slightly weak form of convergence. Okay. Ideally, we would like to stick with pointwise convergence or uniform convergence, but sometimes it may not be possible. We may have to look into the weaker forms, and at least in the L2 sense we can basically describe these things in a subtle way. Okay. So, now we are sort of ready to revisit the earlier theorem that I stated, and we will discuss the proof of the result. We can stop here and I will begin with the next.